today's lecture, we will be looking at Taylor or slug flow regime in particular. So, first of all, let us look at the characteristics of Taylor flow. Taylor flow or slug flow regime is characterized by the regular and periodic flow, as I have written here, regular and periodic flow of bubbles which are of the size of the channel. The picture shown here is for a vertically upward flow, and the bubble is in the black color, and you can see that there is a film on both sides of the bubble which separates it from the wall. So, there is a thin film that separates it from the wall, and the flow of bubble is periodic. So, you have a number of bubbles, and that is why it is also called a train of bubbles or bubble train flow. And in between two consecutive bubbles, so if we look at the schematic of a bubble train flow, we will have something like this, a picture something like this, that one have bubbles moving with a velocity, let us say ub is the bubble velocity, and this bubble is moving with the velocity ub, and in between the bubble we have what we call liquid slug. Okay, because these slugs are trapped between two bubbles, so they will also move with a velocity which is equal to ub, because if they do not, then eventually what will happen, that the two consecutive bubbles, they will come close and eventually make coalesce, or if the slug or the distance between them keep increasing, which does not happen, and if that happens, then its flow is not periodic. So, the slug velocity is equal to the velocity of the bubbles. In microchannels, where the gravity effect is not dominant, so the bubble shape is generally axisymmetric. Okay. So, before we go on to do anything else, let us look at some of the terminologies that might be required to understand Taylor flow. So, superficial velocity, it can be the superficial velocity of the gas phase, superficial velocity of the liquid phase, and it is basically us is equal to q over area of cross section of the channel. Now, if we are looking at gas, then it is USG, or superficial velocity of gas is equal to Q of gas divided by channel cross section area. Similarly, superficial velocity of liquid will be Q of liquid divided by the channel cross sectional area. Okay. Mixture velocity is also called two-phase velocity, and the term Tp comes from two phase. So, UTP is defined as QL plus QG. So, the total flow rate divided by the channel cross sectional area. So, from this we can see this is also equal to UTP is equal to U superficial velocity of gas plus U superficial velocity of liquid. Now, bubble velocity, the bubble will generally be moving faster than the average velocity of liquid in the channel. So, the velocity of the bubble, we generally term it as or represent it using UB, Then homogeneous volume fraction and void fraction, or gas fraction or gas holdup. There are two terms here which represent the volume fraction of gas. So the first term is not necessarily the actual gas volume fraction. So this term represents the ratio of the gas flow rate to the total flow rate when it is assumed or when the gas and liquid are homogeneously mixed. So that means beta is defined here as gas flow rate over QL plus QG. But that is not generally the case in Taylor flow, because the bubble move faster. So the gas velocity will be more than the liquid velocity. So this will also change the volume fraction of, or the average volume fraction of the gas in a channel. So this is this actual void fraction or the actual volume fraction of gas is called epsilon G, or void fraction. That is the actual volume fraction that you see in the fully developed Taylor flow in a channel. Okay, so little bit of history. It is almost 80 years ago, at least that is where I could find, that Fairbrother and Stubbs, they looked at understanding the velocity of bubbles in a capillary. The idea was that they thought that a Taylor bubble can be used as an indicator to measure the velocity of the liquid in the channel. And eventually they found that the bubble velocity is more than the average liquid velocity in the channel. Then in 1961, Taylor did the experiments for a range of capillary numbers. So to remind you, the capillary number is equal to mu u over sigma. So sigma is surface tension between gas and liquid phases. Mu is the liquid viscosity, and u should be ub, bubble velocity. But because in many cases we might not know the bubble velocity beforehand, and there is not much difference, at least the difference between the bubble velocity and the two-phase velocity is about 10 to 15 or 20% at max. So this can often be written, or this is often written as mu L UTP over sigma. So Taylor measured the film thickness for a range of capillary numbers experimentally, and after him this bubble shape has been known as Taylor bubbles. Then in 1961, the same year, Brotherton in his classic paper, he did the theoretical analysis to analyze the shape of the bubble, calculate the thickness of the film surrounding it, and from there find out the bubble velocity and the pressure drop across a bubble. Then because this particular configuration, that a bubble flowing a capillary, this also can mimic the flow of red blood cells in capillaries. Mind you that the red blood cells, they are not exactly like bubble, but they have a membrane and they are flexible particle. However, as a first approximation, one could understand a relatively simpler problem of bubble flow in microchannels. So they looked at to understand, with the motivation to understand the blood flow in capillaries, they looked at Taylor flow. Then in 1971, there are bag, he used it for continuous segmented flow analysis or for segmented flow in the liquid region. And in 1973, Howarth, he looked at radial mixing in the slug flow, and then there have been a number of studies, some of which I have written. The Ratolowski and Chang, they looked at the shape of the bubble numerically, and Kolb and Sairo, they had quite a few papers for application in coating inside a capillary. So the liquid coating in the capillaries, and when you have the liquid filled with the material, or the capillary filled with the material with which it is to be coated, and then the air is blown through the capillary, and the front shape of the meniscus or the interface that forms that edge like Taylor bubble, and that gives you what is the film thickness. So they looked at the problem from this perspective. And in 2000, Ocelus and Kayer, they looked at the film thickness at large capillary number, extending the Brotherton's correlation, who developed a correlation for the film thickness. And after that, in the past 2 decades, there have been a number of studies on Taylor flow in microchannel to obtain film thickness, to obtain heat transfer, for mass transfer applications, or even simple validation of the numerical codes, because when one can do the experiments, one can digitize the flow very accurately, and it can be used for the validation of a say volume of fluid method where the interface is captured. So some of the applications, as I said, it was earlier described to use for measurement of liquid velocity. The concept is still trying to be used, or people are trying to develop multi-phase flow meters based on this concept. Then in chemical processing, for example, catalyst coating, multi-phase micro reactors. If you look at the gas liquid reactions in microfluidics or in microchannels or chemical microprocessing, then about 80 to 90% of the work that you will observe is being done. It might be a gas liquid flow, or liquid flow, or sometimes even gas liquid solid flow. Most of the work is being done in the Taylor flow regime. So it is very important to understand the hydrodynamics in Taylor flow regime. In biomedical applications, the blood flow in capillaries, as I said, this can mimic the same problem of RBC flow in capillary or in microcapillaries. Then the lung airway opening problem. So in the lungs, there is mucus surrounding the walls of the alveoli, and then in between those there is sometimes the mucus forms a liquid plug, and this interface looks like the Taylor bubble. So for example, Professor Grothberg, his group has looked at a number of effects on say the characteristics of this structure, and how what force is required to break this liquid plug, because it is not it can be harmful for the kids in which this problem generally occur. Then in last 2 decades, the gas sparging has been used for removal of fouling in the membrane, and it has been shown that this fouling is most efficient if the gas liquid flow occurs in the Taylor flow regime. So this enhances the microfiltration efficiency in microfiltration, nanofiltration, so in the membrane fouling removal. Then in the electronics cooling, where one want to have the advantage of the high thermal or heat capacity of liquids, and further enhance the heat transfer. It has been it is being used, and its application is being explored in electronics cooling and heat exchangers. In fuel cells, one have gas liquid flow, so one have this flow regime, and in the oil and gas industry, where the channels might not be the straight channel, but there is flow of oil and gas and the displacement of one fluid by the another, there one will observe Taylor flow regime, might be in gas liquid or liquid flow. So it has a number of applications. Now let us look at some of the physics of it. So what we have drawn here is a channel in which the gas is coming from one inlet, let us call it inlet 1, and the liquid comes from another inlet, inlet 2. And we consider a control volume that is represented by the dotted line. And the outlet of this control volume, or the other end of this control volume, we take an arbitrary cross section in the channel AA. In this figure we have taken it where both the phases are present, but one can take it where it is only liquid phase. So let us look at and write the mass conservation equation here. One of the assumptions that we make here is that the flow is incompressible. So that means rho g and rho L are constants. Okay. Mass conservation, if we apply, then we can write mass in the control volume minus mass out of the control volume, and that will be equal to mass accumulation. We are not considering any reaction here, so no generation or sink term will be there. So if we look at the gas phase, then if the gas flow rate is Qg1 at the inlet, so we write it as Qg1, and the density of gas is rho g minus, let us say, the gas flow rate at AA. So Q is volumetric flow rate. So Qg1 rho g minus Qg AA rho g is equal to d by dt of gas volume in the control volume, and we represented by V gas in the control volume into rho g. Okay. So the control volume Vg or Vcv is the total volume of the control volume, and Vgv is the volume of gas in the control volume. Similarly, if we write down the same equation for liquid, then we have QL1 into rho L minus QL at AA into rho L is equal to d by dt, the volume of liquid in the control volume into rho L. Let us say this is equation A and this is equation B, and if we add them but after dividing them by density, so what we do is A by rho G, equation A divided by rho G, plus equation B divided by rho L. You can see that rho G will cancel out from there anyway. So if we do that, then what we will get is QG1 plus QL1. All this is at the inlet, so we can actually remove the 1, and for our better understanding that can be at the inlet minus QG plus, so actually we should have written this earlier itself as at inlet, okay, minus QG plus QL at cross section AA, that will be equal to d by dt of gas volume in the control volume plus liquid volume in the control volume. Okay, so what we end up with is this equation, that QG plus QL at the inlet minus QG plus QL at cross section AA is equal to d by dt of volume of control volume. Remember that volume of gas in the control volume plus volume of liquid in the control volume, because there are only two phases, so that will be equal to volume of control volume. And volume of control volume, as our control volume is fixed, so that is a constant. It does not vary with time, so this term is 0. So that means that QG plus QL at the inlet is equal to QG plus QL at any cross section AA. Now if we divide by the channel cross section A here and the A cross section, so this is U superficial velocity of gas plus U superficial velocity of liquid, and we had defined this QG plus QL over channel cross section. This is equal to UTP or mixture velocity at AA. So this gives a important result that at any place in the channel the two-phase velocity is equal to the gas and liquid velocities. And the assumption that we have made in this derivation is that the flow is incompressible. So this is valid not only for the capillary or the slug flow or the Taylor flow, but for any other flow also. So if you have a flow in a channel, then if you measure the average velocity at this cross section, this is equal to UTP. If you measure the average velocity at this cross section, this is also UTP. Okay, so this is an important result that can be quite handy and useful. As I have said, that the Taylor flow is periodic in nature. So that means if you are doing the experiments and you are in the laboratory or a stationary frame of reference, so then you will observe, if you have a channel and if you are looking at this point, then you will observe, and what I am going to plot is, let us say, with time, the volume fraction. So one will observe that the volume fraction keep changing, so, and it is periodic. So one bubble comes and then another bubble comes, then another bubble comes. So the flow is unsteady, of course, in the bubble frame of reference. Flow is unsteady, periodic in time, at any time instant this is also periodic in space. So if you take any snapshot of Taylor flow in a channel, then you will have the bubble shapes are supposed to be same and periodic. Pardon me for my poor drawing skills. So there is periodic flow of bubbles, and this is also periodic in space. Now, what if we are sitting on the bubble? So if we change the frame of reference to the bubble frame of reference, then the first thing will be that you will have bubble stationary. So when the bubble is stationary, or then what will happen, that you are looking at a different picture. In this case, you have a velocity. If the slug is long enough, maybe the velocity profile is almost parabolic. If not, then you will have some gradients in the liquid, but all in the positive direction. That is what it has been shown here. But if you are in the bubble frame of reference and the bubble is stationary, so the flow is in this direction in the earlier case, but now the bubble is stationary. So let us say there is no and before we describe the periodic flow, let us say because the flow is periodic, so we often take one unit cell, and this unit cell is one bubble and one slug. It can be any choice. You can have the boundaries like this, or for convenience one can have the boundaries that the bubble is in the middle and one half of the slug in the back and one half of the slug at the front. So in the bubble frame of reference, UB is equal to 0. So that means you will have the walls, the actual flow is in this direction, or in the laboratory frame of reference, the flow is in this direction. So when you are sitting on the bubble, you will see the walls moving with minus UB velocity in the opposite direction. And as a consequence, you will also see the velocity profile to be something like this. Bubble is stationary, wall move in opposite direction with bubble velocity, and for a unit cell which is like this, that we have a unit cell which has a bubble plus 2 halves of adjacent slugs, only liquid phase is present, and it has half the channel, but at half the cross section it is coming in and half the channel it is going out. Okay, so if you have if you have noticed in the previous slides, there was another statement that one can see internal recirculations in the liquid slug. So those internal recirculations are basically this, which can be seen in the bubble frame of reference. So it is sometimes quite useful to look at or study the bubble flow or the Taylor flow, analyze it in the bubble frame of reference, because the bubble becomes stationary and then we can analyze number of things on this along this stationary bubble. So we had defined two void fractions, beta and epsilon g, and generally what we have at our disposal is flow rate of gas and flow rate of liquid from the experiments. So that means that we have u superficial velocity of gas and u superficial velocity of liquid, and that gives us UTP, which is equal to u superficial velocity of gas plus u superficial velocity of liquid. But if we want to find out bubble velocity, that is not known a priori. We can also find out beta very easily from the flow rates. These can be the inputs. So beta is equal to Qg over QL plus Qg, or we can also write this, Qg over QL plus Qg, and this is u superficial velocity of gas over UTP. Now we can have a relationship from the mass conservation of gas, that UTP into beta, which is also equal to u superficial velocity of gas, or Qg over channel cross sectional area, that is equal to UB into epsilon g. So if we are able to measure the bubble velocity, so after UB is measured, for example visually, then one can find what is epsilon g. So epsilon g is equal to UTP beta over UB. So this is another important relationship which can be used for analysis of Taylor flow. Now, moving on further, if we look at the bubble shape, the bubble has a front and a tail, and this is a constant thickness film region. So bubble shape is almost cylindrical here, and this film region is, let us say, the film thickness is B. So B is the film thickness. If we apply mass balance or say, then we can write that the and also assume that not mass balance, let us say, we have just found that average velocity equal to UTP. So if we use that relationship here and draw, let us say, the channel radius is R, then we have UTP into pi R squared is equal to U of bubble into pi R minus B squared plus UF, which is flow in the film, into pi R square minus pi R minus B squared. Now, film is generally, film has negligible flow. When we talk about the film, this is, I am talking about the constant thickness film region. So that implies that UF can be neglected. So this term goes away. And what we have is pi and pi also cancelling out. So we have UTP over UB is equal to R minus B over R squared, or R minus B over R is equal to UTP by UB raised to the power 1 by 2. So 1 minus B by R is equal to root of UTP over UB, or B by R is equal to 1 minus root of UTP over UB. You might note that the bubble moves faster than the average velocity in the channel, so that means this number is always going to be less than 1. So this is the relationship for film thickness. So we have seen that if we can find out the bubble velocity, then we can know what is the film thickness. If we find out the bubble velocity, then we can also know what is epsilon g, or in among B, epsilon g and UB. Out of these three, if we can find one parameter, then we can further analyze and find other two parameters by the relationships that we have just now developed. Okay, so let us look at a bit in the flow field in the liquid slug. So when we have flow field in the liquid slug, and I briefly talked about that we have the slug, the velocity profiles in the slug also we have plotted. So let us plot few bubbles here. So if we look at a velocity field in the slug, it will look something like this. Now the question comes, or people are often confused, that it has been written in the literature that it has internal recirculations with them. So the internal recirculations is, this can be decomposed actually, that it can be the slug velocity, the velocity profile that one see is slug velocity plus internal recirculation velocity. That means the velocity in this, because the slug on an average it has to move with the bubble velocity in the front direction. Okay, so its total velocity is such that it moves with the bubble velocity. If we look at a slug, let us say if we have a slug something like this, then the picture in the slug will be something like this. So there is internal recirculation, and that can be seen in bubble frame of reference. So you see that, and in along this there is also a small film surrounding the slugs. So this film may or may not be of the same thickness, that is the film surrounding the bubbles. So what we have is that the slug, few things that we can note about the slug, that the slug move with bubble velocity. Internal recirculations can be observed in bubble frame of reference, and the slug velocity is the sum of two, the internal recirculations as well as the slug velocity. Now next we will talk about Berthatton's problem. So in 1961, in his classical JFM paper, Journal of Fluid Mechanics paper, Berthatton has analyzed the flow of a Taylor bubble in a capillary, and what he was able to do, that using a lubrication approximation, he analyzed the flow behavior around the bubble and used Young Laplace equation for the pressure jump across the two phases near the interface. And from those two equations, he was able to find out the bubble shape and more useful from that he could find out the film thickness, and as we have seen that from thickness we can also find out the bubble velocity and the volume fraction, and he could also find out the the pressure distribution and the total pressure drop across the bubble. Okay, so we will look at this problem a bit in detail now. So first thing he looked at, he considered a long Taylor bubble. And by that what he meant is long cylindrical region in the middle. If you look at the shape of the Taylor bubble, you can fit the front part, which is part of a circle, and that comes because of the Young Laplace equation at the front, and at the back at very low velocities this might be almost same as at the front, but at high velocities you will see that the bubble tail becomes flatter and flatter. So at the back also you have the back of the bubble also you can fit part of a sphere, and in between the film thickness. So what he was able to do, or what he said or he suggested, that we can analyze the two parts of the bubble, front and back, independently. Now, he considered the front. So, for convenience, we will analyze the front part and then use the result for the analysis of the back part. So, if we consider the front of the bubble, then we will look at three regions in the bubble, for example. So one is in the front, which is spherical. Then this region, I have not been able to draw the films to be same, but they are same here, or we are considering axisymmetric bubble. So the constant thickness film region. So this is, if we say this is 1, 2, and let us say 1, 2, and 3. So this is 1, this is 2, and the main region of interest is 3. See, as we have said that the flow in the film is negligible. Flow, and it is cylindrical in nature. So we know that if we know the film thickness, then we know this shape of the bubble. Front, it is spherical. So we need to find, what we need to find is the radius of this sphere. Now we look at this intermediate region or intermediate film, which is between the two. We also consider this in bubble frame of reference. So when we are looking at the problem in bubble frame of reference, then the bubble will be stationary and the wall will be moving with a velocity minus u. So that is why you see these uniform vectors in the constant thickness film region. The channel radius is r, the film thickness is b, and the thickness of the film in the intermediate region, in this region it is considered to be h, and it is varying along the axial direction. So axial direction is x, and considering the origin at the wall, we have x and y, the coordinates near the wall, and these coordinates are in the film region. Now we can apply lubrication approximation. So lubrication approximation is just scaling, that if one of the approximations here is, because the problem is axisymmetric, so if we look at a cross section in the bubble, we have this channel wall and this is bubble interface. Wall, bubble interface, and this is channel cross section in the bubble region. Okay, so the film thickness is b and the channel radius is r, or if we are in the intermediate region, then this channel thickness is h, and the channel radius is r. So when h is very less than r, then for flow in the thin film, we can use planar coordinate system. Also remember that when we have looked at the problem in the bubble frame of reference, then we have been able to convert it to a steady problem. The flow is in the film, the coordinates are planar, and now we look at the some of the further let us look at the pressure jump at different points. So if we assume the pressure just at the front of the bubble in the liquid region, that the pressure at this point is 0 at the front of the bubble in liquid. If the pressure at this point, let us call this point as 1, at this point the pressure is 0, then by Young-Laplace equation, we have a sphere will have a radius of curvature, or the sphere will have a radius r, and the pressure difference across a sphere will be 2 sigma by r. So if the radius of curvature at the front is rf, then we have pressure just near the bubble front, but in the bubble it is 2 sigma over rf. Now note that pressure is almost uniform in the bubble when you compare with that in the liquid region. So when the pressure is uniform in the bubble, so with respect to this point, we have the pressure difference 2 sigma over Rf at the bubble front, and that same pressure will be everywhere in the middle and back of the bubble. So now look at the pressure jump in the middle of the bubble, and if you analyze the pressure jump in the middle of the bubble, then you have P in the liquid film in the cylindrical region. So this is cylindrical portion, and the pressure jump here will be equal to 2 sigma by Rf is the pressure inside, and that is equal to the difference between the pressures is equal to sigma over R minus B. So P bubble minus P liquid is equal to sigma R minus B. So that is why we have pressure in the film region is equal to 2 sigma by Rf minus sigma over R minus B, because the radius, this is cylinder, so the radius of curvature for the cylinder in one direction it is infinite, and in the other direction normal to it, it is radius of cylinder, which is R minus B. So 1 over R1 plus 1 over R2 for a cylinder is 1 over R minus B. So we have pressure jump, and from that the pressure in the liquid constant thickness liquid film region 2 sigma by Rf minus sigma R minus. Similarly, at the back of the bubble, just near the back, we will have 2 sigma over Rb is the pressure difference, and pressure in the bubble is 2 sigma over Rf. So the pressure difference is 2 sigma over Rf minus 2 sigma over Rb. So that will also be the pressure difference there, delta Pb. So this is the pressure distribution at different points in the bubble, and some of it might be used later in the course. So using the lubrication approximation equations, as we said that we can analyze this problem using the planar coordinate system. So here I have written the Navier-Stokes equation for an incompressible Newtonian fluid and at steady state this is continuity, and this is of course in 2D, and this is momentum, x momentum, another one is y momentum. So what we want to look at is we want to analyze is the film in the intermediate region, where it is the film thickness is h and this direction is L. So h is such that h is very less than R, but it is bigger than B. H will also be smaller than the L, where L is the length along the axial direction. So this is x direction, this is y direction. Now if we look at the continuity equation and an order of magnitude analysis, so the Vx over x, which is L, be comparable with Vy over h, and if we write that, then Vy is equal to h by L Vx. So when h is smaller than L, then Vy can be negligible with respect to Vx. So we will not consider, so we will consider or neglect the Vy component in this. So if that is the case, we will also have the flow to be fully developed in such case. So that means that del Vx over del x will also be approximately 0. This is from, we have got from continuity equation. Now let us look at y momentum equation. So this term will be 0 because Vy is 0, all this is going to be 0. The only thing that we get from here is del p over del y is equal to 0. That means p is not a function of y or only a function of x. Okay. In this equation, this term is 0 because Vy is equal to 0. This term is 0 because del Vx over del x is negligible, and this is also 0 because del Vx over del x is equal to 0. So what we have is del p over del x 1 over rho is equal to mu over rho del 2 Vx over del y2. So we have a simplified equation, mu del 2 Vx over del y2 is equal to del p over del x. Let us integrate this. So what we will get is, we can actually write this as total derivative. So we will write now this as total derivative, and d Vx over dy is equal to 1 over mu dp over dx y plus C1. Now the boundary condition at the interface will be, this is gas liquid interface. So if it is gas liquid interface, then we will have zero shear boundary condition, or what we call free slip boundary condition, which means that the shear of the gas at the liquid phase is negligible. So dVx over dy is almost equal to 0 at the interface. So the interface is this. So this is y is equal to h. At y is equal to h, so we will have dVx over dy y is equal to 0 at y over h, 1 over mu dp over dx h plus C1. So this gives us, if we subtract the two equations, we will get dVx over dy is equal to 1 over mu dp by dx into y minus h. Let us integrate it further and apply the boundary condition at the wall. So we had this dVx over dy is equal to 1 over mu dp by dx into y minus h. Let us just confirm it. 1 over mu dp by dx y minus h, and we can integrate it to find out Vx is equal to 1 over mu dp over dx y square over 2 minus h y plus another constant C2. For that we can use the boundary condition at the wall. So if we again draw the problem where we at y is equal to 0 and it is in bubble frame of reference, so we will have wall moving v w equal to minus u. So v at y is equal to 0, vx is equal to minus u. So we substitute that here, then minus u is equal to C2. So that gives us Vx is equal to 1 over mu dp over dx y square over 2 minus hy minus u. So having obtained this relationship, let us now calculate the flux in the film. So if we calculate flux in the film still in the planar coordinate system, we will get q film is equal to integral 0 to h vx dy, and remember this is also equal to so in the constant thickness film region, the film thickness is b and the velocity is minus u. So this q is equal to minus ub. So if we substitute this here, so we got minus ub is equal to 1 over mu dp over dx y cube over 6 minus h y square divided by 2 minus ub, and the integration limits from 0 to h. On simplification we will get minus ub is equal to 1 over, and this is minus u into y here, 1 over mu dp over dx. This is h cube over 6 minus 0, so this will be h cube minus 6 minus h cube over 2 minus uh. So if we substitute here, we will get u into h minus b equal to minus 1 over mu dp over dx into minus h cube over 3. So what we will get is dp by dx is equal to 3 mu u h minus b over h cube. So using the Young-Laplace equation, we can calculate the pressure difference across the, so what this equation is, pressure jump in the intermediate region. So in this intermediate region, P bubble minus P is the pressure in the intermediate region, or the region where we are looking at the flow or where we are analyzing the flow. Is equal to, so this will be sigma over r minus b, so this will look something like this. So it has two radii of curvature, one is in this direction and another one is normal to it, which is in the say cylindrical region. So this is r minus h, so this have been approximated as that b is h is very small, so this has to be sigma over r minus h. But then because r is very small, as we say that r is large than h, so we can write that p bubble, or where p bubble is 2 sigma over r f minus p equal to sigma over r plus sigma d2h over dx2. The other radius of curvature, so this is can be approximated, this radius of curvature can be approximated as d2h by dx2, and the other radius of curvature normal to it is sigma over r minus h, which we have approximated as sigma over r. So if we differentiate it, we get dp over dx is equal to sigma d cube h over dx cube minus here. So if we substitute that in the film region, then we will get this equation. This is d cube h over dx cube is equal to 3 mu u into h minus b over h cube. And if we non-dimensionalize it by having two non-dimensional coordinates eta and psi, so h is approximated as b into eta. So let us substitute that here. We will get d cube eta b over dx cube is equal to 3 mu u over sigma is capillary number. So you have 3 Ca into h minus b. So we can write this as eta minus 1 over eta cube, and here you will have b squared. So if we further write this, they will have d cube c eta over d over b into 3 Ca power 1 by 3 cube is equal to eta minus 1 over eta cube. So what we have done is approximated this. This is x over b. So if we look at x over b over 3Ca to the power x, this is psi. So what we have defined as psi is equal to x into 3Ca power 1 by 3 divided by b, or x is equal to b 3Ca power minus 1 by 3 psi. So we have got the equation, final equation, d cube eta over d psi cube is equal to eta minus 1 over eta cube, which is a very useful equation, and we will look at its solution in the bubble front and bubble back region in the later classes. So what we have looked at today is looked at what is the basic flow characteristic or flow behavior in the Taylor flow, and the useful relationships between film thickness, bubble velocity, and epsilon g. So B, epsilon g, and UB relationship. We have also looked at that UTP is the average velocity in channel, which is equal to QG over plus QL over channel cross sectional area. Then we have looked at Berthatton's problem. So in the Berthatton problem, what we did is applied lubrication approximation in film region and substitute pressure from Young Laplace equation and then obtain a relationship between d cube eta over d psi cube is equal to eta minus 1 over eta cube, where eta is h by b. So this is the radial coordinate or the coordinate in the transverse direction, and eta is and psi is x over b 3 Ca power 1 by 3. So this is a coordinate, non-dimensional coordinate in the axial direction. So the solution of this equation will give us the bubble interface. Of course, we will need to apply a few boundary conditions to it. Okay. Thank you.